generalized force and momentum. We have introduced Lagrange's equations, or the equations of motion, which are given by a system of n differential equations. Lagrangian is defined in terms of generalized coordinates, q's, and generalized velocities, q dots, and is equal to kinetic energy minus potential energy. Our notation is that the q set of q's is denoted by this braces. Now, normally, we expect that the kinetic energy will be just a function of velocities. And potential energy will be just a function of generalized coordinates. Let's find derivatives, partial derivatives that go into the Lagrange's equations. Let's start with the first partial derivative of Lagrangian with respect to generalized coordinate q sub I. This partial derivative becomes derivative of just potential energy with a minus sign, minus partial derivative of u with respect to the coordinate q sub I. Now, this partial derivative is a gradient, spatial derivative, gradient of minus u. And we know from Newtonian mechanics that this is force. When you can write force as a gradient of a function, then you are dealing with conservative forces. Therefore, we can interpret this term as a generalized force. Generalized force. Why generalized? Because it needs not have units of force. Just like generalized coordinate doesn't have to have units of length, for example, angle, so generalized force doesn't have to have units of force, newtons. For example, torque. Next, let's look at the partial derivative of Lagrangian with respect to velocities. So in analogy, we can write that partial derivative of Lagrangian with respect to velocity now becomes just partial derivative of kinetic energy with respect to velocity. Again, if we use analogy with Newtonian mechanics, for example, we can write kinetic energy for 1 degree of freedom, say position x, as half of mass times velocity squared, which gives us partial derivative of kinetic energy with respect to velocity as mass times velocity, which we can identify as a component of the momentum in this direction. So therefore, we can interpret partial derivative of Lagrangian with respect to velocities as generalized momentum, or the component of generalized momentum. Now, let's rewrite Lagrange's equation, and we will see a clear meaning of Lagrange's equations and its connection to Newtonian formulation. We have from Lagrange's equations that partial derivative of Lagrangian with respect to generalized coordinate q sub I is equal to full-time derivative of partial derivative of Lagrangian with respect to velocity q sub I dot. In other words, what we're seeing on the left-hand side is generalized force, and on the right-hand side we have rate of change of generalized momentum. Rate of change of generalized momentum, which very much looks like second law of Newton. But of course now we're dealing with generalized coordinates, generalized forces, and generalized momentum.